Okay, mermaids and gentlemen, let's see what we can do with this here Chemistry Solutions Review Guide 2019. All right, list the three factors that increase the rate of solvation for a solid. Well, you know them as shake, bake, and break. But more importantly, you should know them as stirring or agitation. Stirring/agitation, heating, and increasing surface area. That's what breaking does, by the way. When I make things smaller, I increase the surface area. If I have a cube and I cut it in half, I've increased the surface area by one plane. So if this is 2 by 2 and this is a 4 centimeter square plane, if I cut this in half, then I've increased the surface area not just by 4 square centimeters, but by 8 because there's two sides. Well, if I keep crushing, I'm doing exactly that. I'm increasing the surface area. If I increase the surface area, there's more surface area for the solvent to affect the solute, and that's what we're after in solvation. Okay, suppose you are given a Ki salt water solution. Identify the solute. Well, the Ki salt is the solute. And water, if you don't know, is the universal solvent. So almost always water is a solvent. Rarely is water going to be anything other than a solvent. All right, what is the molarity of an aqueous solution containing 75 grams of sodium hydroxide and 500 milliliters of solution? First thing you have to know to do a problem like this is you have to know what they're asking. Like you have to know if they're asking for a molarity, which we know the formula for this, liters of solution. I'm not writing out the entire moles of solute over liters of solution equals molarity. That's big M. Little m is something different in chemistry. We have to know if we're looking for a percent by mass, which is solute over solvent plus solute. By the way, solvent and solute together is also called a solution. Times 100 equals percent by mass. You got to know what they're asking. Well, if I see what is molarity, that's kind of obvious. You know they're asking what is molarity. The second thing you have to know is, do you have the parts of this? This says 75 grams of sodium hydroxide. Well, is 75 grams of sodium hydroxide moles? No, it is not. So I know that I'm going to have to at least convert one thing, 75 grams of sodium hydroxide, into moles of NaOH in 500 milliliters of solution. Also, this is in liters. It is not in milliliters. The simple way, I'm just going to tell you, divide it by 1,000. So if I divide 500 by 1,000, that gives me 0.5 liters. It has to be in liters. This has to be in moles. Does that make sense? I hope so. All right. I've been saying that a lot. I got to stop that. Maybe y'all can ask that back at me when I ask it of you. Okay, so I have 0.5 liters, so I have what's on bottom, the denominator here. And they're asking me what is the molarity. I need the moles on top, so I'm going to erase this and do a little conversion over here. You remember dimensional analysis. It is not 3 boxes. I am not going from grams to moles of something else. I'm going from grams of sodium hydroxide to moles of sodium hydroxide. That is just a dimensional analysis cross, or 1 box if you need that. Okay, so I have 75 grams NaOH. The rules for dimensional analysis have not changed. Grams NaOH. And as soon as I write grams where chemistry is concerned, now dimensional analysis in physics and any other thing, you might be converting grams to kilograms, grams to other things, but the only thing we convert grams to in chemistry right now is moles, and it is 1 mole of that substance. All right, so G stands for grab my periodic table. Na 23, O 16, so that's, what do we got there? 39 plus 1, an H. So, yeah, 23, 39, 40. 40 grams, right? Is that right? Am I right? Yeah, I'm right. 40 grams of NaOH. So, 75 on 75 divided by 40 equals 1.875 moles over 0.5 liters equals what molarity? So I'm going to divide that answer by 0.5, and it's going to be quite obvious that I'm going to get 3.75 molar. That's it. That's my answer, 3.75 molar. I'd love for you to use units, because when you get into the habit of not using units and just writing numbers, you're going to write a 75 up here, and you're not even going to realize it's grams because you don't have any units beside it. So it's real easy for me to write 75 and 0.5 liters below that and think to myself that, oh, I'm doing this correctly because that's moles. But if they give you 75 grams, that grams should chase that number around wherever that 75 goes. So please, 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 I'm begging you, be good with your units. Molarity. All right, how many grams of potassium sulfate would be dissolved in 2 liters of a 1.5 molar solution? Okay, so we have, this is our formula again. It's a molarity formula, obviously, because they've given us a molarity, they've given us liters, and they're asking us how many grams. But we're going to calculate how many moles and then go to grams, right? Right, okay, so we have 2 liters x moles equals 1.5 molar. 1.5 times 2 is 3, so I have 3 moles of K2SO4. Moles of K2SO4, 1 mole of K2SO4. I'm kind of getting ahead of myself because I'm going to grams of K2SO4. And obeying that rule of grams in chemistry, if I write grams, it's 1 mole below that. Ooh, K2SO4, let's see what the weight of that is. Let's see, potassiums are 39.1 times 2. A sulfur is 32.1 plus 32.1. And plus 4 oxygens, 4 times 16. Enter. So I get 174.3. If I'm wrong, I'm sure y'all will correct me on Monday. 174.3 grams per mole times 3 equals, I get 522.9 grams of K2SO4. That is my answer. Grams. I did answer how many grams. And y'all should get in that habit too. When you find what you think is your answer, go back and look at what they say how many grams. Oh, well, my answer's in grams, so I'm there. Okay, explain how you would prepare a 1 liter solution of 2.5 moles of KNO3. So, if I just take the molarity formula and I go, okay, I'm making 2.5 molar 1 liter solution, and I need X number of moles. Well, 2.5 times 1 is 2.5, so I need 2.5 moles of KNO3. Okay, so here's the tricky part. They say a 1 liter solution. That does not mean that I put 2.5 moles of KNO3 into 1 liter of water. If I have a 1 liter container and I put 2.5 moles of KNO3, which is how many ever grams it is, 40, 50, 60, 70, 80 something. If I put 80 grams of stuff in here and then pour 1 liter into this 1 liter container, the water is going to come out. So the way to describe what you're doing is you are putting 2.5 moles of KNO3 into a 1 liter container, then adding water to the 1 liter mark. It's going to be less than 1 liter of water. You're adding less than 1 liter of water. This is the key phrase here. I'm adding water to the 1 liter mark, or whatever target they're giving you. If it's 2 liters or 5 liters, you're adding water to reach that 5 liter mark, or whatever you're trying to reach. You're not adding 5 liters. I'm not adding 1 liter of water. If I add 1 liter of water, this thing will overflow. Okay, I hope I've emphasized that enough, and if I have, then I'm sorry, because that's just test questions, man. That's just test questions. Okay. How much NH4Cl will you need to make a 2 molar solution? Well, again, it looks like a molarity question, but sneaky. If this is the molarity formula, I have moles of solute over liters of solution. All they've given me is my molarity. They haven't given me, so these are both X. So can I solve number 6? No, I cannot solve number 6. Number 6 is undoable. There's just too many. I mean, I have 2.0 molar equals X moles over X liters. You got to give me something. I can only solve for one variable, right? Okay. 6. Let's go to 7. Colligative properties depend on the concentration of solute particles, but not the type. Right? Not the type, but not type. I mean, it doesn't matter what you're adding. It's completely on concentration of your solute particles. Does that make sense? That's the definition of a colligative property. It is a property that depends entirely on the concentration of solute particles. The boiling point of pure water is 100 degrees Celsius. What would most likely... Oh, hey, the lights are out. I don't know when they put my lights. Freaking timer. But I guess let's see how long this video's been on. Every 15 minutes or so, they're going to just cut the lights off on me. Where was I? The boiling point of pure water is 100 degrees. What would most likely happen to the boiling point if 15 grams of KCl was added to a beaker containing 500 grams of water? They're trying to trick you into thinking that this is a math problem. This has nothing to do with math. This has everything to do with colligative properties. You know that when water is trying to liberate itself from a pot of boiling water, remember, these things get so active because they're heated up. They're heated up and they're moving around so fast that they're trying to jump out of the solution. Now, what happens to KCl when I drop it into solution? Well, it breaks down into its ions, right? It is an ionic compound. We have positively charged potassium and negatively charged chlorine. Now I want you to imagine that this partially charged positive hydrogen and this partially charged negative oxygen have both a potassium attached and a chlorine attached. Can this get out of the water? The answer is no. It's carrying too much luggage. So instead of heating it up to 100 degrees and all of a sudden it becomes vapor, now I can heat it above 100 degrees. So the boiling point would increase. Man, I hate to cut this off right here, but I'm really trying to keep these videos under 15 minutes. So what I'm going to do is I'm going to cut it off right here. I'm going to continue number 8 on the other side in just 2 seconds. All right.